Hi, Mr. Kowalik here. Welcome to the second part of the sedimentary rock unit. Today we'll be looking at formation of sedimentary rocks, how they form, and a little bit of classification of them on how they look on the reference table. So remember to follow along in your notes, fill out your notes, and do all your assignments. Let's get going. So last time we learned that sedimentary rocks form due to erosion and weathering, and as we move those rocks through water, we understand that they come to a large body of water. They're deposited at the end of a stream or at the end of a lake, or sometimes they're washed around on the shores of an ocean, or maybe they're drugged somewhere by a glacier. In any case, once they've stopped moving, they are deposited and they tend to layer up. And each season that goes by produces different layers. And for thousands and thousands of years, layers get deeper and deeper and deeper. And as you can see in this diagram here, the very bottom layer is going to be the oldest, and the very top layer is going to be where the deposition is currently happening. So over thousands of years and thousands and millions of pounds of pressure from the overlying bedrock above it, these layers beneath it are getting squashed down, which is a term we call compression. And in some cases, there's a mineral that is left behind through the evaporation process, in which case those rocks are being cemented together. In this image here, we can see that happening. We see the particles being carried by wind or water, loosely packed on top, and then densely packed on the bottom. So it's these densely packed particles down here that are getting compacted and possibly cemented together through the process which forms sedimentary rocks. Here we get to see the same thing happening, but now we throw some names of sedimentary rocks on. You can see in the bottom we have conglomerate, which are these large particles mixed with some smaller particles. Then we have sandstone and limestone and siltstone and mudstone. And on the top here we can see this fish finally passed away and is now incorporated into the mudstone, which over time another layer could come on top and form over him, and thus starting the fossilization process. So this is how we form fossils in sedimentary rocks. In this image we can see a number of places where sedimentary rocks will form. In the bottom diagram you can see some rivers and streams emptying out into the ocean or a large body of water, forming deltas and spits and lagoons like we learned in the last couple of units. Up here you can see a glacier melting and that stream forming a floodplain where we have a deposition of sedimentary rocks, and a swamp over here where there's more deposition, and we form sedimentary rocks here as layer upon layer upon layer gets deeper and deeper. In this video, they talk about that compression that forms a sedimentary rock. I suggest you come back and look at it. It's about 3 minutes long. So finally, the last part on formation and how they form is a process called cementation, or gluing of the particles together. Cement, or cement as some people say, is like glue, where we have some particles and we add something in between. All right. In the second picture over here, you can see the blue is something in between that's holding the particles together. Compaction does not involve cement. It's a reduction in the spaces through the process of adding pressure. And that reduction of air in between these particles increases surface area contact and holds things together. Here we're not doing that, we're just adding a glue. The glue comes from evaporated waters that have minerals or certain particles in them that, when evaporated, leave behind those minerals like quartz and calcite, hematite, which would glue these together. So on the Earth Science Reference Table, we're talking about land-derived inorganic sedimentary rocks. All of these are either compacted or cemented together, the top half of the reference table. When we get to the bottom half, we're talking about different processes that form those rocks. We'll get into that in a little bit. So we're talking about the inorganic land-derived sedimentary rocks. It's the first type of rock. Again, we'll talk about chemically and organically derived in just a minute. But the term derived means where it came from. So inorganic land-derived means it came from the land, so it started out in a stream or in a glacier and was deposited, and it's not from a living thing. The second half of the chart does involve chemically derived, where there's an evaporation process happening and we have layers of minerals stacking on top of each other, producing a thicker mineral deposit, which is now considered a sedimentary rock. Or we have the organically derived, where we see rocks forming that were once or coming from a place that was once alive. For instance, a shell from a mollusk can be considered a sedimentary rock if it's glued together in a large formation. We call that limestone. So the term inorganic land derived, we see sediments or clasts coming from pre-existing rocks like igneous, metamorphic, or even other sedimentary rocks that have been weathered down into smaller pieces. The material that's been weathered is typically a silicate mineral, because back in the mineral unit we learned that a majority of those minerals are in the silicate oxygen tetrahedron group, so they contain oxygen and silicon as their main constituent. So if the silicate group of minerals is the main part of the sediments that build sedimentary rocks, when we organize them, the composition is going to be mostly quartz and feldspars. Some clays and fragments of other rocks are included, but we do see a lot of quartz because it is the most readily available mineral on the surface of the earth. So how is the composition useful for identifying these rocks? It's not that good. We can come back to this slide and see that if we just look at the fact that the rock has quartz in it, it could be any of these rocks here, and that's not a good enough indicator. So the fact that silicate minerals are present, which is quartz and feldspars and clays, is not good for identification. What are we going to use instead? Well, we're going to use particle size. In this case here, we can see sand particles that would make up a rock called sandstone. We measure the grains to be between 0.2 and 0.006 centimeters in size, which indicates they're sand-sized particles, so we're going to call it sandstone. It's interesting here that the color is not useful, because these four pictures have four different sands from four different beaches, and we have a light color, pink to a white to a green to a black. You can see a big variety of sand colors producing different sandstones. So color is not helpful. What it's made of is not helpful. Again, we're going to particle size as the main identifier. So we come over here to this column in the reference table. Pebbles and cobbles and boulders embedded in sand, silt, and clay. So we have large particles, which are going to make up our conglomerate and breccia. Then we have sand particles, that's going to make up our sandstone. We have silt-sized particles, going to make up our siltstone, and clay-sized particles, which is going to make up our shale. So here we can see actual examples of those. Conglomerate, very large particles all glued together. Some cobbles and pebbles and boulders. Maybe not boulders, but probably some pebbles. Maybe a cobble. And we have breccia down here, which are large particles all glued together as well. Maybe here's a pebble and some larger and smaller particles. The big difference between these two rocks is that conglomerate has rounded particles that are probably pulled downstream, and we have breccia, which is angled particles, which were probably transported by a glacier. They're the same particle sizes, the same fact they're glued together, probably looks like the same glue in between. Dark red's probably hematite. The big difference is the angled versus round. That's the only difference between them, and that's why they have two different names. As we move down the reference table from conglomerate and breccia, the next largest particle is our sand particle. Sand-sized particles are between 0.2 to 0.006 centimeters. You can actually pretty much see the particles themselves. Pretty big, looks like sand glued together, like a chunk of kinetic sand. The smaller the particles get, the move down the reference table. So we go from sandstone down to siltstone. Silt is very fine, almost too hard to see with the naked eye, but there's something there. But it's bigger than clay. And we have a range of 0.006 to 0.0004 centimeters in diameter for the particles, producing siltstone. It's going to be very similar to sandstone, but just a smoother finish to it. You can't really see the particles. Then finally clay. And clay, you can't see the particles at all. They're pretty much invisible to the naked eye, 0.0004 centimeters in size. And those particles glued together, clay, without any moisture in it, basically, or compacted down, is considered shale. And then, as you can see here, we have some fossil impressions in the shale, which we'll see more as we go. So I'm going to stop here before we get into the next half of the reference table. We'll leave that for part 3, looking at the chemically and organically formed rocks and how they form and what they are, how they look on the reference table. So make sure you answer the questions, do the notes or the castle learning that we have assigned for this part of the sedimentary rock. See you soon.